This video is on section 7.1 notes, estimating a population proportion. So at this point, when we've gotten to chapter 7, we're pulling everything together with the goal of doing a statistical analysis. So here it says a statistical inference is concerned with making decisions or predictions about parameters. So to kind of explain what that means a little bit more, if we think about the reason why we collect data, is typically there's some sort of population or a large group that we want to know something about. Maybe we want to know something about all of the people in the United States, but it's not time efficient, it's not practical, it's not cost efficient to talk to every single person in the United States. So we take a sample and we look at that sample and we find statistics, not parameters, we find statistics about that sample, and then we hope that those statistics are representative of the population. And that's what this is talking about. So we're concerned with making decisions or predictions about parameters. We're making predictions about the population mean, the population standard deviation, and the population proportion. There are two basic categories of methods for making statistical inferences about these parameters. The two methods are estimation and hypothesis testing. So estimation is what we're going to be learning about in chapter 7. Hypothesis testing is what we're going to be learning about in chapter 8. Estimation is estimating or predicting the value of the parameter. Hypothesis testing is making a decision about the value of a parameter based on some preconceived idea about what its value might be. So first, when we look at the different types of estimates, we have point estimates. Point estimates are the sample proportion which is notated using p hat. P hat is how you say that. It's the best point estimate or single value estimate of the population proportion. Which we notate using P. So for example, in a Sallie Mae survey of 950 undergraduate college students, 53% of the students said that they take online courses. Based on that result, find the best point estimate of the proportion of all undergraduate students who take online courses. So using this definition of point estimate, we would say, well, our best point estimate is going to be that sample proportion, that p hat. So if it's the sample proportion is 53% of the students said they take online courses, our best estimate is that 53% of all undergraduate college students take online courses. That's all the information we have. That's all we can guess from it. So we would say that p hat was the 0.53 or 0.53 proportion of the students take online courses, and p hat is the sample proportion. And here we would say that the sample proportion is the best estimate of the population proportion. Another way we can make estimates is by using confidence intervals. And confidence intervals are ranges of numbers. So not just one specific number, like a best point estimate, but a range of values that is used to estimate the true value of a population parameter. It uses the sample proportion p hat to estimate the population proportion p. So similarly, we're going to use the same information, we're going to use p hat, but we're also going to pull in some other information that we're talking about in a second so we can have a range of answers. So it's not very likely that the actual percentage of all undergraduate students who take online courses is 53%. It's probably around 53%. Maybe it's 54, maybe it's 57, maybe it's 49%, but it's probably not exactly 53%. So a confidence interval allows us to get a little bit closer by having a range of values. So here it says our confidence level is the probability that the confidence interval actually does contain the population parameter, that it actually is correct, assuming that the estimation process is repeated a large number of times. So here I'm going to show you how these probabilities, or the probability that the confidence interval actually contains that number, how they calculate these probabilities. So we have 3 confidence interval levels that are typically used. They use 90%, 95%, and 99%. So if our confidence level is 95%, then the probability is in a normal distribution is this middle 95%. And the outliers are that 5% that's on either end. So if we take the 0.05 and we divide it by 2, then we have 0.025 on the lower end of our range and 0.025 on the upper end of our range of these values that could be outliers or could be outside of our interval. So if I look for that critical number using my chart, I want the z-score that gives me the probability 0.025, 0.025 right here, and it's negative 1.96. Negative 1.96. Okay, and then the area over here is also going to be 0.025, but whenever we measure it using the standard normal distribution table, remember the areas are always measured from the left. So I can't measure this area of 0.025, I have to measure this complementary area. And the complementary area is 1 minus 0.025, which is 0.975. Okay, so if I look for a 0.975 probability, 0.975 is right there. That's 1.96. Makes sense. There's some symmetry there. Okay, so if you are using a 95% confidence interval, then your critical value is 1.96. And we could use those same methods to find the confidence level for 90% and 99%. I'll spare you going through and showing you mathematically how each of those work. But the critical value for 90% is 1.645. And the critical value for 99% is 2.575. And so these values are important. You want to make sure to write these in on the table because we're going to be using these in our formulas today. So now to construct a confidence interval, you're going to use the formula p hat minus the standard error or the margin of error and p hat plus the margin of error. And then here's the formula for margin of error. So this is your critical value. P hat is that probability of successes, whatever the example problem describes. Q hat is the complement of that. So when we talked about that example before, we said the probability that undergraduate college students take online courses is 53%. So the complement of that would be 47%. So you do P hat and its complement, and then N is the number of trials, right? And then beneath that, it says to interpret a confidence interval, we write the sentence. So we are 90% confident or 99% confident or 95% confident that the true population proportion of students undergraduate students who take online courses is between 0.5 and 0.6 or something like that. All right, so let's go ahead and look at a specific example so you guys can see this in action. So the first thing I'm going to do is I'm just going to describe the P, the population proportion that we're actually trying to find, that we're trying to take this P hat and use it, extrapolate it to describe something else. So it says a random sample of 300 adults was taken, and 192 of them said that they always vote in presidential elections. So we are curious to know about the population proportion of adults who always vote in presidential elections. And the way that we're going to do that is we're going to look at this sample and we're going to come up with a confidence interval of where we think the population proportion probably is. So our P hat, the proportion of the sample that votes in elections, is 192 out of 300. Okay, so I'm going to go ahead, sorry about that, I'm going to go ahead and do this math real quick. 0.64. Okay, then I have Q hat, which is the complement of that, so 1 minus 0.64, 0.36. And I have the number of trials, 300. Okay. It says to construct a 95% confidence interval. So my critical number, or Z sub alpha divided by 2, my critical number at alpha divided by 2 is, for 95%, 1.96. Okay, so I'm going to do P hat plus or minus the lower end and the upper end, the margin of error, which is Z sub alpha divided by 2, so it's that critical value, times the square root of P hat times Q hat, divided by the number of trials, or the number of people talked to in this case, how big the sample is. Okay, so I just have to figure out the lower end. P is between two numbers, so P hat minus the margin of error and P hat plus the margin of error. Okay, so there's the minus version. And then I'm going to type it in again and do the plus version. So what this means is that the true population proportion for adults who say that they always vote in presidential elections is probably between 58.6% and 69.4%, somewhere in between there. For the sample, it happened to be 64%, but the true population is probably between 58.6% and 69.4%. That's what this confidence interval means. Right? And you can write the confidence interval as an inequality like this, kind of using this portion of the formula right here, or you can write it in interval notation and write it as 0.586, 0.694. Both of those are good. Okay, so we found the confidence interval. Next, we want to interpret the confidence interval. So we're going to write our sentence out, and we're going to fill in the blanks. So I'm going to say, we are 95% confident that the true population proportion of adults who say they always vote in presidential elections is between 0.586 and 0.694. Okay. An article in American Demographics reports the percentage of adults who say they always vote in presidential elections is 67%. Agree or disagree? So here, 67% is in between those two values. It's between 58.6% and 69.4%. So I don't disagree. But for them to commit to 67% it's hard to say 67% for sure because did they talk to every single person in the United States? Probably not. So I would say I don't disagree. But I don't necessarily agree either. So it could be 67%, but is not guaranteed. So I definitely don't disagree, but I'm not saying that I agree either. So kind of in between. Okay, let's try another one. So this one says, suppose the number of successes of something observed in 500 trials of a binomial experiment is 27. Find a 99% confidence interval for P. Interpret the confidence interval. Okay, so P is the population proportion of successes. So P is the population proportion of successes. P hat is the sample proportion of successes, which we know was 27 over 500. .054. Q hat is the complement of P hat, so 1 minus 0.054. .946. N is the number of trials, or how big the sample was, so 500. And then our critical value has to do with our confidence interval, which was 99%. And so the value that we're going to use for our critical value is for 99%, so 2.575. 2.575. Okay? And then I'm going to go ahead and use the formula. So I know that I'm doing P minus the margin of error and P plus the margin of error, which is why I put plus minus last time. And then here, this is the formula that I'm using. Okay, so I'm going to say P hat, which is 0.054 plus or minus. And I have that critical number, which was 2.575, times the square root of P hat times Q hat divided by N. P hat times Q hat divided by N. So 0.028 0.080, and you can write it as an inequality like this, or you can write it as an interval. Both are good. And then it says, the instructions say to interpret the confidence interval, and so we're going to write our sentence while filling in the blanks. So we are 99% confident that the true population proportion of successes lies between 0.028 and 0.080. So the sample was 5.4% probability of success, or percentage of success, and the true population proportion we think is somewhere between 2.8% and 8%. So somewhere between there, but our sample was 5.4% successful. So that's what we're saying.